can think about this particular cell as being created as the sum of two possibilities.
Right.
Either for the row that it came before, either the object was included or the object was excluded.
Right.
So the way to include the object is n minus 1 choose k minus 1 ways.
Right.
And the way to exclude the object is
n minus 1 choose k.
Exactly.
So that actually encodes what mathematicians would call as a recurrence.
Exactly.
So this recurrence that we derived, really, of n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k is actually an example of a very fundamental combinatorial principle. Isn't that right?
Absolutely. And here's my favorite example of a principle. It's called the pigeonhole principle.
Ah, sounds great.
And the reason it's my favorite is because it's very intuitive. So here's the example I'm going to show you.
Okay.
We have 5 pigeons, and they are flying home. These are carrier pigeons, so they're flying to their home. There are only 4 homes.
Right, right. So somebody might get left out, is that right?
Unfortunately, if there are more objects than there are boxes, and only one thing is in a box, then there's stuff that doesn't get assigned.
Okay, good.
Okay. But to make that pigeon happier, we're going to say that everybody has to be put in a box.
Okay.
And what that's going to do is it's going to force that pigeon into some box that's already occupied.
Right, right.
So the pigeonhole principle in this case is going to say that if there are 5 pigeons in 4 boxes, some box, no matter how the pigeons distribute themselves among the boxes, some box is going to contain at least 2 pigeons.
Right. So some box might actually have 3 pigeons, right? I mean, that's also possible.
Right, but the box with 3 pigeons also contains 2.
That's right.
Okay, so that's at least 2.
Yes.
And in fact, if we take the average of the number of pigeons to the number of boxes, okay, what the pigeonhole principle says is some box contains at least the average.
I see. So the average number of pigeons per box here would simply be the number of pigeons, which is 5, divided by the number of boxes, which is 4.
But because we can't have a quarter of a pigeon in some box.
Right. No pigeons are harmed during the making of this show, right?
Right.
Yes.
Okay. They're discrete objects.
Yes.
We have to round up.
Right.
So that tells us we're going to get 2 pigeons per box in this case.
Right. At least 2. So these basic principles that we've been outlining, these are numbers that are easy to compute. Like we've been finding formulas, in fact, computing the numbers of pairs of hats or computing things like the average for the pigeonhole principle.
In particular because they're small.
But as we get more possibilities, we begin to experience what we've been calling this combinatorial explosion. And we're going to see an example of that now as poor old Charlie gets a new itinerary. So let's take a look. Charlie seems to have found his solution. At least he's crossing one off, and that's a start. Except now his boss has called and added more stops to his itinerary. 8 more to be exact. Now he's got 12 places to organize. And it's beginning to look like there are so many possible ways to go, he'll never find an efficient route that will let him get home in time. Poor Charlie, he really seems to have his hands full here. He's suffering from what we were calling before a combinatorial explosion.
Well, poor Charlie doesn't have a prayer in the world of answering his question definitively. Okay, but there are ways that we can cleverly approach a problem and organize the information so that we can reduce the amount of work that needs to be done.
Oh, is that right?
Here's an example for you. Okay, the setup is we have a keypad with 10 digits, and we want to input a 3-digit code to unlock the door. Okay. So if you were to do this in sort of a very natural, methodical method, you put in 000, you put in 001,
make your way through,
and you test every number from 0 to 999. Okay, and that might take you a while.
And that's 1,000 codes, and I have to hit for each code. I hit it 3 times. That's 3,000 pushes, right?
Exactly. Okay. Now, if you use something called a De Bruijn sequence, okay, this is a way of organizing this information so we really reduce the amount of work that we're going to do. We're going to cut the amount of work by a factor of 10. In a De Bruijn sequence, we can organize the list of numbers in such a way that every 3 digits that we want to read is a different set, a different combination. So you might start with 000, test those first three,
Okay.
and then hit 1, that's going to be 001 is now going to be
I see.
tested.
So I have this. So I'm sort of sliding a window along. First is 000, and then I would slide it one thing, and then, in other words, I'd press a 1, so that would mean 001 is the next code that I was testing.
Exactly.
Okay.
And now by organizing it in this fashion, we've reduced the amount of work by a factor of 10. So if it took 5 hours to test all 1,000 numbers, it's now going to take on the order of 30 minutes.
Oh, great. Math to the rescue.
So in fact, De Bruyne sequences are not only useful to get into a door, it's also being used right now in genomic analysis.
Yes. Genomics generally is a big user of combinatorial work, the sort of discrete units of the genome, and we have an example of that here. Let's watch.
I'm Terry Gasterland, and I'm a professor of computational biology at University of California, San Diego. I'm in the marine biology department. I have collaborators in New York, and I have collaborators here in Oregon. You can think of DNA in many different ways. If you're a computer scientist, you can think of it as ones and zeros, or you can think of it as 4 letters, A, C, G, and T. If you're a biologist, you think of DNA as a long, complex molecule that is made of each of the compounds that A, C, G, and T represent. A genome is the specific bundle of DNA that's in a particular cell. So we can think of DNA as being paragraphs, words, sentences, where a genome would be the specific book that is you. DNA sequencing is the process of trying to read the letters that are in the book. So sequencing is the process of fragmenting that DNA into little tiny pieces and reading a little bit of each of the fragments. And now you've got all these 500, 700 letter words, and you need to fit them all back together. Early on, when people started trying to sequence genomes, people came up with the most interesting and innovative ways to do it. Then there was the process of directed primer walking. So randomly go into the genome, do a read, and then design a little probe that will put you into the next, at the end of that read, and then keep reading. And it turned out that the problem there is that genomes are very repetitive. So every one of these ran into combinatorial problems. And it turned out that the idea Craig Venter was really pushing finessed all of this combinatorics. Take the whole entire genome, chop it up into lots and lots and lots of little pieces, and take reads off every one of those and do so many that you have enough information to fit those pieces back together. For any given book, if you will, you have multiple copies of the book, and one you're ripping in half at chapter 1 and the other you're ripping in half at chapter 4. If you do enough of them, it will cohere into one. Given this fragment and given this fragment, 200 bases overlap, so we'll put them together and see if we can put the next one in. And if those two overlap and then you have a third one that comes in and it matches, you know you have it right. With a human genome, which is 3 billion A's, C's, and G's, and T's, you need to be a little smarter. So now you set all sorts of heuristics. So you say, well, let's take every pair of reads that overlaps by at least, say, 100 letters, and they have the identical 100 letters. The problem is there's always sequencing error. For every one of those comparisons, you're computing all these details about it. So that is the problem that the computer has to solve as it's doing assembly of all of these pieces. When I first started in looking at genomes, the only genomes that were being sequenced were one-celled microbes, bacteria and archaea. Proteins from one organism would have absolutely no match whatsoever in the next organism over. So there seemed to be proteins that were absolutely unique to each of these organisms. So that made people step back and say, well, we need to sequence more organisms and fill in all the holes and the gaps in this tree of life. So now we go from one-celled organisms to more complicated organisms with several or many cells, or even with differentiated cells like a sea urchin or a human. Gene by gene, we can look across the evolutionary tree and ask which gene in sea urchin goes with which gene in zebrafish, and that goes with which gene in human. And by studying when that gene turns on and turns off during development or in maintenance of a healthy organism in sea urchin, that tells us something about how it might be working in human.
Wow, so genomics, this is a particular example where combinatorics has really helped us. You know, it's allowed us to simplify a problem, and it's really given us a purchase on how to do things. But there are actually problems which are combinatorial in nature, which we still don't know how to solve. Isn't that right?
Well, like Charlie, for instance.
Poor Charlie, yep.
He's in what we call a traveling salesman problem.
Yes, he is.
The idea being you're given a certain number of cities and you want to travel, starting from one city,
Right.
you want to travel to all the cities getting back to where you started
Right.
in the most economical fashion.
Right.
Okay? Now, if there are a small number of cities,
Right.
the analysis is not difficult.
Right.
So if Charlie only had 3 cities,
Uh-huh.
okay, there are only 2 possibilities. Either he goes clockwise from where he
Right.
is, or he goes counterclockwise.
Right.
Okay?
So each route has a cost as well.
Each route has a
Right,
cost.
okay.
But now if we add a city to that,
Uh-huh.
okay, his 2 choices
Oh, I see. Yep, it's
go
starting to grow. Yes.
6.
Yep.
Okay?
Yep.
If we add another city,
Okay, it's getting worse. Yes.
it goes from 6 to 24.
I'm seeing a pattern here. Is there one, in fact?
Oh, there absolutely is. If we jump to 10 cities, there are now over 350,000 possible organizations to his route.
And that factorial number is coming in here again, isn't it?
Exactly. So 10 cities
Uh-huh.
gives us 9 factorial possible routes.
Okay, 9 times 8 times 7 and so on. Okay.
If we jump to 25 cities,
Okay, that really looks like a problem here.
there
All
are
right.
billions and billions of routes. And no matter how clever we are, there's no way we can look at every single one and find the best or fastest possible route.
All right, well, Jenny, this was great. Thanks.
My pleasure.
So Charlie is left with too many possible solutions, more than he can calculate with a simple map and a pad of paper, or even his laptop. But sometimes the path is clear, and sometimes the right way to organize information is the way that leads us home.
Hi, Princess.
Daddy.
Happy birthday to you.
Kids, cats, sacks, and wife. Emily, we're going to St. Ives. Yay!
Our lives are constructed out of seemingly endless possibilities. We make choices so we can be more efficient in what we do and where we go, so we can unlock the secrets of the human genome, or simply solve a math riddle. The answer to the riddle, by the way, is 1. I'm the only one going to St. Ives. The other combinations we'll save for another time.